In the name of Allah, the Merciful, the Compassionate. Lecture 2, Metallurgical Aspect of Corrosion. Structural features. Number 1, crystal feature. Crystallographic arrangement for atoms in lattice. When heterogeneous nature for metallic material surface led to sites of corrosion and susceptibility of these sites to environment provide regions of corrosion. Groove features, grain boundary, subgrain boundary, and lattice defects, imperfections, surface atomic topography. Three deformation features: slip markings, twin bonds, stacking faults, and dislocations arrays. This figure schematic illustration of atoms located in the different sides on metal surface. This schematic illustration of dislocations of more reactive atoms from king side, eventually uncovering a more noble atoms. It is easy to remove the atoms from lattice defects, from kinks, from trays, from twin bonds, and slip kinks. Figure 4.8 image taken from microstructural evolution of a binary alloy with 100 slip planes, crystalline orientation undergoing dissolution. The row indicated a 1-1-1 paste. The crystal planes play a role in corrosion zones and in gorge of corrosion. Figure surface imperfections in a crystal. Impurity in surface, king step, adsorbed ion and edge dislocation, screw dislocation, monomolecular bit. Can be shown that monomolecular bit for surface imperfection in crystals. Real materials, free surface, free surfaces. Free surfaces have a structure that may differ from the bulk solid and also a different lattice spacing. This real surface containing ledge, kinks, and surface thicknesses provide location with stronger bonding than the trays and are therefore four sites for atom addition during crystal growth or surface contamination by non-lattice atoms. Can be noticed that trays frequency step, trays, king side, these lattice defects are location for corrosion. Surface features on growing or dissolving crystals. Adsorbed atoms can be removed from the surface when the aggressive environment subjected to the materials. King phrase surface nucleation of a crack at the surface. Dissolution can be initiated at the surface of materials. Precipitation, ions in solutions. Dislocation can be occur as a result of heterogeneous character for chemical composition and metallurgical structure. These dislocations in metals, titanium, and B in silicon in figure 422. Dislocation in metals, A in titanium and B in silicon. These dislocations can be occur as a result of heterogeneous character for chemical composition and metallurgical structure. In metallurgical structure, impurities precipitates secondary phases from phase transformation and composition variations. This metallurgical structure can be contain impurities, precipitate, and secondary phases from phase transformation and composition variations. Maybe contain segregation of solute and dislocation solute interactions. This each bits case study of pitting at the surface for metallic materials because strain field surrounded for dislocation. Can be noticed that anode and cathode. These dislocations provide to suffer chemical reaction and darkened the microstructure. This is the plane, maybe 111. Dislocation line and Baker's factors. Effect of metallurgical structure on corrosion. Apparent width of grain boundary and B H bit with dislocations, which grain boundary have high energy state and more reactivity. Grain boundary have high energy state and more reactivity with the environment. These large strains and small strains when materials subjected to metalworking, maybe rolling, extrusion, wire drawing, deep drawing. In large strains, lamellar boundaries, but in small strains, dense dislocation, cell block, dense dislocations, wall, and micro band. When the microstructure subjected to high strains provide to more corrosion can be occur than the materials which subjected to small strains, because high strains provide stress concentration in the microstructure. Corrosion. Some materials form in oxide scale. Other materials form bits when they oxide. Both oxides are detrimental, but the consequences for the two types of corrosion are different. Both oxides are detrimental, but the consequence for the two types of corrosion are different. How does this corrosion affect the performance of the materials? Number one, scale oxide reduces the thickness of the materials. A reduced thickness can cause an overload of the material, which can lead to failure. Bits from surface cracks. The cracks can reach a critical crack size, leading to failure as seen in our fracture lecture. Scale oxide reduces the thickness of the materials. Bits from surface crack. The crack can reach a critical crack size, leading to failure. Okay? Bits led to critical crack size. Corrosion and relationship with dislocations. Dislocation form grain boundaries as a network and act as pipes for diffusion, which is required for corrosion. Dislocation form grain boundaries as a network and act as pipes for diffusion, which is required for corrosion. The type of dislocation in body center cubic, in face center cubic, in hexagonal closed bracket are different. Dislocation in body center cubic materials do not react with each other to form extended network, so they remain localized. Those dislocations at the surface tend not to extend deep inside the material. Those corrosion remains at the surface to form a scale. The metallic material which have body center cubic, alpha iron, barium, molybdenum, niobium, tungsten, chromium. Dislocation in face center cubic materials can react with each other to form extended networks that can extend deep into material from the surface. Those corrosion can penetrate the material to form bits. Which materials have face center cubic? Nickel, silver, copper, gold. These dislocations in these materials or in these metallic materials can react with each other to form extended network that can extend deep into the material from the surface. Those corrosion can penetrate the material to form bits. Corrosion and dislocations. Two dislocations in a face center cubic material can react with each other to form a third dislocation, such as the example for two dislocation can react to form a third dislocations. Emission of dislocation from layers in a grain boundary as observed in transmission electron microscopy. Face center cubic dislocation interaction. As seen in the figure, two dislocations can interact to form a third dislocation, which can extend the dislocation network below the surface of the material, allowing a pathway for corrosion product. The examples for phase center cubic metallic materials: nickel, silver, copper, gold. These materials ductile materials. Corrosion and dislocation. Two dislocation in a body center cubic. Body center cubic: alpha iron, barium, molybdenum, tungsten, niobium, potassium, chromium. Less ductile material but stronger. These metallic material less ductile but stronger metallic materials. Two dislocation in a body center cubic material cannot react with each other to form a third dislocation. For examples: number one, led to annihilation. Two, too high of energy to form. Figure 454. Pile up of dislocations against grain boundaries, or dislocations being emitted from grain boundary sources. These microstructure in a cover observed by H bitting. Stacking faults in gallium phosphate. Stacking fault in calcium phosphate. This stacking fault in microstructure features. Number 4, microstructure. Microstructure of materials contain impurities, precipitation or precipitates, and secondary phases from phase transformation and compositional variations. When concentration change in metallic materials provide segregation of solute and impurities of grain and dislocations. Dislocations, segregation of solute and impurities of grain and dislocation. Solute interactions, relationship between electrochemical and metallurgical aspect of electrode potential and polarization phenomena, macroscopic in nature, not give fine details to caustic and mechanistic features. The electrode potential, polarization phenomena, macroscopic in nature, not give fine details to caustic and mechanistic features for corrosion process. Specific metallurgical heterogeneity provide two: local cell action. Local cell action provide local anodic and cathodic actions, as well as provide all total for local anodic and cathodic actions provide to local cell action. Structure sensitivity of corrosion reaction. Microstructure parameters: low effect in uniform corrosion rates, high effect in localized or preferential corrosion. This structure sensitivity of corrosion, microstructure, low effect in uniform corrosion rates, but high effect in localized or preferential corrosion. The figures explain homogeneous and segregated structure. discontinuous precipitate, and as well as continuous precipitate. Continuous precipitate provide high corrosion resistance, but discontinuous precipitate led to low corrosion resistance. Homogeneous structure led to high corrosion resistance. Segregated grain structure led to low corrosion resistance. This figure explains desired background for information about microstructure dependent reactivity in corrosion process. When a metal solidifies during casting, the atoms which are randomly distributed in the liquid state arrange themselves in a crystalline array. This ordering usually begins at many points in the liquid in casting, and as these blocks of crystals or grains meet, there is a mismatch at their boundary. When the metal has solidified and cooled, there will be numerous regions of mismatch between each grain. These regions are called grain boundaries. Grain boundaries have high energy state but high reactivity. High reactivity grain boundaries provide regions or zones to corrosion. Grain boundary in polycrystalline metal, two-dimensional representation. This grain boundary high energy state and high reactivity in corrosion process. Atomic mismatch region, high energy state and greater chemical reactivity. This grain boundary. Microstructure, microgalvanic cell between different phases, for example between ferrite and cementite in carbon steel. Cementite is intermetallic compound which is more stable than ferrite solid solution. Cementite which more stable than ferrite solid solution. Cementite is cathode while ferrite is anode in carbon steel. Dark area is cementite while bright area is ferrite. The microstructure for carbon steel, ferrite and cementite. Cementite Fe3C, Fe3C cementite. Cementite is intermetallic compound which more stable than ferrite solid solution. Led to cementite is cathode while ferrite is anode. Microgalvanic cell. The upper figure explains bulk material and segregant materials. The bulk material, notice that I core and I bulk and I segregations. The material which segregation contain in the microstructure will provide to regions of corrosion attacks, led to low corrosion resistance. But bulk materials not contain segregations provide high corrosion resistance. The lower figures explain segregations after exposure led to high corrosion sites. Corrosion process consists of two stages: nucleation or initiation stage, non-homogeneities, kinks, leads, trays, jerks, point defects, changing for perfection of surface films, impurities at the surface. These features provide nucleation or initiation zones. Situation: metallurgical non-homogenization and non-homogenization in chemical composition provide high intensity of chemical reactivity. Figure: the surface of a metal is complex, inhomogeneous mixture of many different types of materials. Inhomogeneous mixture contain grains, grain boundaries, crystal defects, inclusions, as well as precipitate inside grains. Growth and propagation stage. Kinetic factors, film formations, diffusion reaction, passivity and polarization. Kinetic factors, film formation, diffusion reaction, passivity and polarizations. Examples: chromium carbides at grain boundaries. This chromium carbide Cr23C6, cracks forming along embrittled grain boundaries. Crack forming along embrittled grain boundaries. N3O4 stainless steel, highly localized attack for stainless steel. N3O4 in seawater led to pitting, and local galvanic action depend on chemical composition of the matrix and chemical composition of the precipitates. Depend on chemical composition of the matrix and chemical composition of the precipitate, led to local galvanic cell action in 304. More examples: desensification in a brass alloy, linear rate of penetration perpendicular to the surface is very much greater to the lateral penetration through the lattice. In this case of chromium carbide at grain boundaries, non-uniform metallurgical features and non-uniform in chemical composition provide situation of high intensity of chemical reactivity. Provide situation of high intensity of chemical reactivity. Grains are more stable than grain boundary due to the arrangement of atoms, so grain boundaries are anode and the grains are cathode, anode corroded. This figure explains what is the difference between a grain and the grain boundary in corrosion process. Grains are more stable than a grain boundary due to the arrangement of atoms, so grain boundaries are anode and the grains are cathode, anode corroded. Ex situ morphology analysis. Cipher corrosion and for right phase slightly edge this boundary, seen that the corrosion process in phases. Figure 7.23, micrograph of a metal near a stress corrosion fracture, showing the many intergranular cracks formed as a result of the corrosion process. Micrograph of a metal near a stress corrosion fracture, showing the many intergranular cracks formed as a result of the corrosion process. Corrosion control by application of metallurgical principles. Number 1, use of high purity material, use of alloying additions, effective heat treatments, and use surface coatings. Figure depending on the material and environment. Electrolyte and materials, oxide dissolution, localized corrosion, maybe de-alloying, grain boundary process, multi-phases, surface chemistry, dissolution, repassivation, and depassivation, this mass transport, the reaction between material and environment, maybe contain local stress. This figure explains the steel in rust case. Can be seen that anode and cathode in water droop in upper figure. In lower figure, the reaction between steel and environment in rust case. Schematic representation of the corrosion mechanism for steel. Fe change to Fe plus 2 electrons. Crystalline state to ionic state. O2 plus 4 electrons plus 2 H2O led to 4 OH. Fe plus 2 OH negative equals FeOH by 2. 4 FeOH by 2 plus oxygen led to 2 Fe2O3, 2 Fe2O3 plus 4 H2O provide rust of carbon steel. A high purity. Role of metallurgical features. One of the best examples of improvement of corrosion resistance of a material found in the result achieved by reducing the sulfur content of a plain carbon steel. Corrosion attack on steel greatly reduced when its sulfur level is low. Lead and zinc die casting alloys also has a marked effect on the corrosion characteristics of the material. If the lead exceeds 0.002%, it precipitates at the grain boundaries and produces increased density of intergranular corrosion. The lead and zinc die-cast alloys also has marked effect on corrosion characteristics. In stainless steel 300L has a maximum limit of 0.03% of carbon. This reduces the possibility of sensitization as a result of welding and heat treatment. In stainless steel 316 contain 18% of chromium and 8% of nickel and 2.5% of molybdenum. stainless steel 316 contain chromium more than 12%, which this person is required person to form stable passivity. The nickel content, when the increase of content of nickel increase the stacking fault energy, which engorge the cellular dislocation distribution more than planar arrays of dislocations, where the cellular dislocation distribution in dislocation morphology are less susceptible to environments which reason to corrosion. The dislocations arrays, stacking fault, other lattice defect in microstructure are recorded. Regions of localized attack and can be the sites for crack nucleation in corrosion process. Surface structure and atomic topography. All these metallic surfaces not flat and uniform, even the perfect atomic surface, which can be rough and irregular surface, maybe contain kings, lathes, trays, extends different types of surface sides, which have different chemical properties. Maybe normal sides in closed backed planes, trays, H for partly closed planes, lathes or stibs, kings or jokes, point defect at the surface. As a result, this point defect at the surface led to adsorbed atoms or vacant lattice sites. Maybe sites of intersection of dislocation with the crystal structure. Sites of interaction of dislocation with the crystal structure at the surface. It is easy to remove the atoms from kings or lathes more than another surface sites. The following shows the effect of purity of aluminum on corrosion by hydrochloric acid. When pure aluminum, relative corrosion rate is low. When purity 99.998, 1 relative corrosion rate, but when 99.2, 30 relative corrosion rate. The figures 7.11 implementation of a defect exposing to copper atoms where reaction with the chloride environment. Alloy additions. It is possible to improve the corrosion resistance of certain alloys by specific alloying additions. Greatly for stainless steel, more chromium percent above 12% led to corrosion resistance of stainless steel. Corrosion resistance also may be improved by changing the electrochemical potential of the second phase in alloy. For example, the addition of magnesium or chromium to aluminum alloys. In these alloys, the intermetallic compound Fe aluminum. In lower paragraph, the intergranular sensitization of stainless steel due to the formation of chromium carbide at grain boundaries can be prevented using alloying addition. In these alloys, it is possible to add columbium or titanium, which selectively ties up the carbon as carbide. Not forming chromium carbide, maybe niobium or columbium carbide or titanium carbide rather than chromium carbide. Eliminating chromium carbide formation and the sensitization of the alloys as well. The addition of chromium, particularly to nickel and iron based material, increase their high temperature oxidation resistance. This Cr23C6 and this depleted area. Chromium boundary, 80% of chromium, Cr23C6, depleted area, cathode area and anodic area. Diagram showing the depleting phenomena in the grain boundary. Lower figure explain the grain boundary contain depleting phenomena. Poor of chromium zone and rich chromium zone. Chromium depletion region anode. Chromium carbide precipitation. This grain cathode. But the chromium depletion region act as anode. Heat treatment. It has been discussed later that is possible to modify the structure of metals and alloys by heat treatment. By control, maybe etching precipitations. The etching temperature for optimum mechanical properties of an alloy may reduce susceptibility to intergranular corrosion. Often it is important to sacrifice some mechanical properties in order to improve corrosion resistance. It has been shown recently that stress relief greatly improved the resistance of 300 series stainless steel to stress corrosion. Of course, the stress relieving must be below the temperature of sensitization 427 degrees Celsius. High zinc process susceptible to stress corrosion in the cold working state also have protected effectively by stress relief. Heat treatment can be used to prevent or decrease the corrosion process. Corrosion rate for AZ91D die cast as a function of exposure time can be explained that corrosion rate millimeter per year degrees when control of the microstructure of this alloy AZ91 die cast. Surface coating for corrosion control. Because the corrosion reactions occur at metal environment interface, it is logical that the interposition of barriers between the substrate and the environment would influence the corrosion rate. Various types of barriers are commonly used for corrosion control, including a wide range of metals, inorganic and organic materials. Surface coatings is very important to corrosion control. Figure intergranular corrosion of 7075 T6 aluminum adjacent to steel fastener. The microstructure subjected to environment led to remove of coating surface coating over the substrate. This removal of coating led to local cell action at the surface, provide to corrosion process. The effect of homogenization on microstructure features and corrosion behavior of cast copper-nickel alloys. The case study for metallurgical aspect of corrosion. Homogenizing is a process wherein prolonged high temperature soaking is used to reduce the extent of chemical segregations. The homogenization used to reduce extent of chemical segregation or coring, which occurs as a natural result of solidification in copper-nickel alloys in casting. It is applied to copper-nickel alloys to improve the hot and cold ductility of cast belts for mill processing, and occasionally to casting to meet specified hardness, ductility or toughness requirement. It is applied to copper-nickel alloys to improve the hot and cold ductility of cast belt for mill processing, and occasionally to casting to meet specified hardness, ductility or toughness requirement. The aim of the present work was to characterize these alloys metallurgically and study the corrosion behavior before and after homogenization. The purpose of this view to explain the corrosion behavior before and after homogenization. Phase diagrams for nickel copper alloy system. Relationship between segregation and structure. An estimate of extent of interdendritic alloy, because when solidified, the cast of copper-nickel alloys provide dendritic structure. This interdendritic alloy element segregation can be obtained with the aid of special equation below. CS equals KC naught 1 minus F 2 power K minus 1, where CS alloy contained variable within dendrite, C naught average alloy contained, K equilibrium distribution coefficient, and F fractional distance from dendrite center, F equal to 0 to center of interdendritic volume, F equals to 1. Schematic plot of alloy element. This is distant across dendritic arm. This equation Cm equals K, C naught 1 minus F K for K minus 1, K equilibrium distribution coefficient, F fractional distance between dendrite arm, center and midpoint between adjacent dendrite arms. This C naught alloy composition, Kappa eutectic composition. This Cm dendrite arm and dendrite arm in microstructure of copper-nickel alloys. The phase diagram for the copper-nickel system, as shown in figure 2.1, was used to determine the fraction liquid Vs temperature at equilibrium for 30% of nickel and 70% of copper. The partition coefficient K, the ratio between composition in the solid and the liquid, Cs divided by Cl, was 1.6. For ease of calculation, in non-equilibrium freezing, it was assumed that this ratio remains constant during solidification. This assumption predicts less segregation than will actually occur for the copper-nickel alloys. The equation for 2 may be rearranged to obtain in expression form. VL fraction liquid equals CS divided by 48 to power 1.67, where FL fraction liquid equals 1 minus F for solid. FL equals 1 minus F solid. The copper-nickel phase diagrams explain the melting point of copper equals 1084.5 degrees Celsius, and nickel melting point for nickel 1455 degrees Celsius. This alpha copper nickel, the copper nickel phase diagrams. Figure 1, secondary dendrite arm spacing. Copper percent and copper and nickel percent in segregation can be occur in copper-nickel alloys. Area rich in copper and another area poor in copper. Area rich in nickel and another area poor in nickel. Segregation can be occur in copper-nickel alloys. This dendritic arm spacing equals L2 divided 5 dendritic lines. This L1 equals L1 divided 7, and dendritic arm spacing equals L2 divided by 5. This copper atom percent and can be calculate the nickel atomic percent in dendritic arm spacing. This program software can be used to determine the dendritic arm spacing for copper nickel alloys and other materials which can be half the dendritic structure, in which the dendrite arms are rich in nickel and the inter-dendritic regions are rich in copper. Such single-phase microstructure are highly susceptible to solid phase. Diagram for nickel copper alloy system. Fraction cracking, liquidation cracking, and in particular ductility dip cracking. The distribution of nickel in dendritic regions is different, more different from dendritic regions distribution of copper. Can be seen that segregation in dendritic structure, rich in nickel and poor in nickel, rich in copper and poor in copper in dendrite arm spacing. Isothermal section of copper nickel chromium ternary equilibrium diagrams at 930 degrees Celsius. The alloy copper-nickel with addition of chromium. The purpose of this alloying element addition to provide more corrosion resistance. The effect of diffusion in the solid is to reduce the amount of microsegregation that occurs during solidification and is dependent on the alpha factor. The effect of diffusion in the solid depends on the alpha factor. Alpha equals 4d s times f divided by d square, this equation 4.4, where in homogenization a useful parameter that calls the index of residual microsegregation, that is equals Cm minus Cm maximum solute concentration of element in interdendritic space at time t. Maximum solute concentration of element in interdendritic spaces at time t minus Cm small, minimum solute concentration of element in center of dendrite arms at time t, C divided by C star m capital, maximum initial concentration of element, minus C star or C dot m small, C dot m small, minimum initial concentration of element. This parameter that calls index of microsegregation or index of residual microsegregation. This parameter can be applied in copper-nickel alloys, in 90-10 copper-nickel alloys, 90 copper, 10 nickel, 70-30, 70 copper, 30 nickel, 75 copper, 25% of nickel. The dendritic structure is a basic characteristic of these ingots, which often provide more reliable aid to interpretation of casting conditions than the grain structure of the ingot. The dendritic arm spacing increases with increasing solidification time. When solidification time increases, the dendritic arm spacing increases, and the average dendrite arm spacing at the center is coarser than that at the outside of the billet. The result may be explained by the following equation, which was determined by the curve fitting techniques. D dendritic arm spacing equals 30 times R rate of cooling 2 power n times C to power n, where D is the secondary dendrite arm spacing micrometer, R is cooling rate 100 degrees Celsius per minute in conventional casting, C is nickel content atomic percent. The properties of dendrite is affected by the cooling rate and structural integrity. Cooling rate and structural integrity. The local cooling rate during solidification is determined by the design of the component and by the process conditions. When higher cooling rate also strengthen the dendrites generally increase with higher cooling rate for as cast material, but the effect is reduced or non-extent for heat-treated alloys. Ultimate tensile strength and ductility is highly related to the coercions of the microstructure and generally increase with high cooling rate. Then ultimate tensile strength and ductility increases with higher cooling rate. Optical micrograph of 1910 carbon-nickel alloy as cast. Can be noticed that the dendritic structure. And optical micrograph in figure 12 of 80-20 carbon-nickel alloy as cast. Optical micrograph of 75-25 carbon-nickel alloy as cast, and figure 14 optical micrograph of 70-30 carbon-nickel alloy as cast. Figure 16 optical micrograph of 90-10 carbon-nickel alloy after exposure to 3.5 NaCl plus NH4NO3 solution for 288 hours, showing attack of dendritic structure. Samples were polished but not etched before exposure. Figure 17 optical micrograph of 80-20 carbon-nickel alloy after exposure to 3.5% of NaCl plus NH4NO3 solution for 288 hours, showing attack of dendritic structure. Samples were polished but not etched before exposure. Figure 18 optical micrograph of 75-25 carbon-nickel alloy after exposure to 3.5% of sodium chloride plus NH4NO3 solution for 288 hours, showing attack of dendritic structure. Samples were polished but not etched before exposure. Can be noticed that the corrosion attack at the surface of carbon-nickel alloys by transverse section. The corrosion attack in dendritic arm spacing is more clear in features in this figure. Typical potentiodynamic plot of carbon-nickel alloys as cast in 3.5% of sodium chloride solution for 90-10 carbon-nickel, 80-20 carbon-nickel, 75-25 carbon-nickel, 70-30 carbon-nickel, and chromium modified carbon-nickel. When chromium modified carbon-nickel led to low corrosion resistance. Low corrosion current density led to high corrosion resistance. The chromium modified carbon-nickel in potentiodynamic plot provide low corrosion current density led to high corrosion resistance. The microstructure of carbon-nickel alloys after homogenization. The microstructure remove from segregations by homogenization. The distributions of copper and distribution of nickel, and remove dendritic arm spacing. The dendritic structure change to grain structure. The grain structure have high corrosion resistance, but the dendritic structure have low corrosion resistance. Typical potentiodynamic polarization plot for copper-nickel alloys after homogenization in 3.5% sodium chloride solutions. The chromium modified 73 alloy have low corrosion current density, led to high corrosion resistance than other alloys. References for this lecture. Thank you so much.